Welcome to this session on the layering method in ANSYS Fluent, a key part of the Dynamic Mesh Complete tutorial series. As always, the link to the previous tutorial is available in the description box. Make sure you watch it for better understanding. And if you need project or thesis support, my contact details are also provided in the description. In this lesson, you will learn how the layering method works inside the Dynamic Mesh framework. We'll understand its two modes, height-based and ratio-based, explore split and collapse factors, and finally walk through a real-world application on a wave generator using Dynamic Mesh plus VOF. The layering method is one of the simplest yet most powerful approaches to handle mesh motion where the boundary moves in a structured direction, like pistons, walls, wave paddles, or valves. Instead of deforming mesh cells, layering adds or removes layers of cells next to the moving boundary to maintain mesh quality. In Fluent, the layering method comes with two control options, height-based layering and ratio-based layering. Both determine when to add a layer or remove a layer depending on how much the boundary has moved, but they do it in slightly different ways. Understanding that difference is essential for getting good mesh behavior. Let's look at how Fluent decides the way new layers are created. When a layer is stretched or compressed, Fluent compares its height with an ideal height that you define. Based on that, it either adds or removes layers. Now, the two modes, height-based and ratio-based, control how these new layers are formed after a split. With height-based layering, the new cells created after splitting have a uniform fixed height. This makes it perfect for simple linear motion where the mesh spacing is consistent. With ratio-based layering, the new cells maintain a smooth height ratio compared to the original mesh. This is very helpful in curved or graded meshes such as cylindrical domains where the cell size is not uniform. Fluent manages mesh quality using two key controls, split factor and collapse factor. When the boundary moves outward, the layer next to it starts stretching. If it stretches beyond the limit allowed by the split factor, Fluent automatically creates a new layer by splitting the existing one. This prevents the cells from becoming too elongated. When the boundary moves inward, the layer starts getting compressed. If it becomes too thin, based on the collapse factor you set, Fluent removes that layer and merges it with the next one. This avoids extremely small or skewed cells. Together, the split and collapse factors help Fluent maintain smooth, high-quality layering as the boundary moves. We start in Design Modeler working on the XY plane, where I quickly sketch a rectangle sized 1 meter by 0.5 meters. Using the Surface from Sketch tool, that simple sketch instantly becomes a 2D surface. From here, we jump into the meshing module, where this surface will form the base mesh that we'll animate using dynamic layering in Fluent. Now let's move on to the meshing stage. First, I apply face meshing with quadrilaterals. So we start with a clean, structured mesh pattern across the rectangular domain. Next, we refine the mesh using edge sizing. I select the two vertical edges and set the number of divisions to 25. I also changed the behavior from soft to hard. This tells ANSYS to strictly enforce the division count, making sure the mesh stays uniform and perfectly aligned along those edges. Then, I select the top and bottom horizontal edges and apply 100 divisions. Again setting the behavior to hard so the spacing is fully controlled. Now comes an important concept, biasing. I choose the bias type. Biasing changes how element sizes grow along an edge. Instead of evenly spaced elements, biasing lets us cluster elements toward both ends. The bias factor is set to 5, which means the element size ratio between the largest and smallest cells is 5:1. Inside ANSYS Fluent, solution is changed to transient solution. After that, I enable the dynamic mesh model. Here, I turn off smoothing and keep only layering activated because our motion is purely one directional and is best handled by adding or removing layers of cells near the moving boundary. When I open the layering settings, you'll notice the collapse factor is 0.2. I changed it to 0.4. Now that the dynamic mesh settings are configured, the next step is to define the actual motion of the moving wall using a user-defined function or UDF. In Fluent, I go to user-defined, functions, compiled, and here I load the C file named wave.c. This code file contains the mathematical expression that controls the time-dependent motion of our moving wall. Next, I enable the option Use Built-in Compiler. This allows Fluent to compile the code directly inside the software without needing an external compiler setup. After that, I click Build, which compiles the UDF and checks for any errors. Once the build is successful, I simply click Load and the function becomes active inside the simulation. Now we move to the final part of the setup, creating the dynamic mesh zone. Since the motion has already been defined through our UDF, I simply click on Create Dynamic Mesh Zone, and from the list of zones, I select the moving wall as the boundary where the mesh layering will take place. Under the meshing options, I enter the cell height value of 2 mm. This cell height is extremely important. It tells Fluent how thick each layer should be when it generates or removes layers during motion. After entering the value, I click Create and then Close. With the dynamic mesh zone created, the next step is to visualize the motion before running the full simulation. To do this, I click on Display Zone Motion. This shows a live preview of how the moving wall will oscillate based on the UDF we loaded earlier. It's a quick way to confirm that the boundary motion is correctly defined and behaving exactly as intended. Next, I move to Preview Mesh Motion. This feature is extremely useful because it animates the actual mesh deformation over a series of time steps, showing how layers will be added or removed as the wall moves. In the preview, you can clearly see the mesh stretching and compressing only near the moving boundary, while the rest of the domain remains stable. This is a good indication that the dynamic mesh layering method is working correctly and that the cell heights and collapse factor are properly configured. Running these previews ensures the motion is smooth, the mesh quality is preserved, and the setup is ready for the final simulation. To see all of this in action, we'll apply the layering method on a wave generator. In this demonstration, the piston-like boundary moves back and forth, and Fluent uses dynamic mesh layering plus VOF to generate accurate periodic waves inside a multi-phase domain. The link to the complete step-by-step tutorial is provided in the description, so make sure to check it out and follow along. Before we close, a quick note. We also provide project and research assistance for students, professionals, and industries. Whether you need help with CFD, FEA, thermal analysis, optimization, dynamic mesh, multiphysics, or advanced simulations in ANSYS, Abacus, Star CCM+, SolidWorks, OpenFOAM, and more, We support academic projects, final year work, MTech PhD research, industrial case studies, and simulation-based consulting. If you need guidance, collaboration, or simulation support, feel free to contact us. Your project success is our priority. And if you found this tutorial helpful, make sure you like, subscribe, and turn on notifications to stay updated with our upcoming tutorials and CFT and FEA videos. Thank you for watching. See you in the next video.